now. I've given 1 to 2 talks a year, so I'm probably getting close to my 20th time up in front of this group. We do have a record of this, I just haven't counted it up. Quick background on me. Got interested in astronomy in 2nd grade, finding a book about constellations by H.A. Rey. And I found out later that it's the Curious George creator. And like all the little characters pointing at constellations look like monkeys. So I started to study that through elementary school, got my first telescope before I got to middle school. And by the end of elementary school, I was helping Boy Scouts get astronomy badges. So went through college, astronomy and physics, meteorology and climatology degrees as an undergraduate. I was there for 7 years. They said, go get an advanced degree. So I chased tornadoes in Oklahoma for a while and got a master's there and went to work for NASA for 17 years as their senior science education specialist under the Earth and Space Science Mission Directorate. I had to say that all the time. And so when COVID came along and James Webb Space Telescope needed another $1 billion, money shifted all around NASA, and I was given 6 months warning that, well, your position's going away. So now I teach at my kids' school up in Loveland, and I teach just about everything math, science, and oddly, I'm teaching PE this year. So anyways, so that's my background. Pardon? Oh, no. I make the kids do it. I just stand there with my whistle. So now I didn't know what a cushy job PE teacher is. It's really nice. All right, so I've definitely covered theories of everything and string theory off and on for the last 15 years here. And we're going to get the history of it and like that. There's been definitely exciting times in string theory and then kind of stall times. Since the last stall time, things got even a little darker. I'll cover that in just a minute. But about half of this is just review and basics of what all these things are. I'm going to assume you don't know what a string is, what dark matter is, what dark energy is, why we're having trouble with gravity. I'm gonna rehash it all. So if you're new to this, I'm not assuming you know anything or been to any of my other talks. Then about a quarter of it will be kind of laying the groundwork for the new Swampland approach. And that's a weird name, landscapes and swampland, but it'll make sense. And the last quarter will be where we get to the new string theory stuff. Really take a lot from science popularist. He's got a great podcast called Mindscape, and he's an amazingly intelligent person. I can barely keep up with him. And then Kumran Vafa is the main proponent for Swampland approach to string theory. All right. So a theory of everything, ATOE, is what physicists have been going for a long time. It's the goal. Einstein was even trying to do it. He was trying to unify gravity and electromagnetism, and was sketching on it right almost to the end. And we're still fighting this battle. Right now, what we're interested in doing, a theory of everything doesn't explain why you're here tonight or what you had for breakfast. A theory of everything is concerned with what links the 4 forces and our 3 families of 4 particles that we get when we smash things together or just go buy something at IKEA. So on the force front, we have, I keep pushing the wrong button, I just want laser. The strong nuclear force these all have particles that carry that force, and that's called the gluon, because physicists have humor in how they name things. It holds the protons and neutrons together and other similar particles that are composites. They're made of other smaller things. So if you want a proton, you need to have 2 up quarks and a down quark. If you want to have, and they're held together by the gluon. If you want a proton, a neutron, you get 2 down quarks and 1 up quark. So kind of neat stuff like that. Things they started figuring out in the 20s and up to the present day. Electromagnetism is what builds your reality. So the fact that the floor is solid and has a color and the windows can be seen through and the air is transparent and it's all electrons pushing against each other and exchanging photons. It makes everything around you except the sense of gravity, your reality. The weak gauge bosons, again, wrong button. Weak gauge, that gives us radioactivity, so it breaks apart in certain circumstances the nucleus of the atom, and then gravity with its graviton. We, in our day-to-day life, have electrons, and then these up and down quarks making protons and neutrons is almost everything we experience. The rest of this is pretty crazy stuff that we get out of very carefully observing what happens when we smash things together. Right, superstrings. Superstring theory is a very specific type of string theory that uses different kind of symmetries. So symmetry, really simple, is if I have a sphere and I rotate it, it still looks like a sphere. So that is symmetrical in all the ways I could rotate it. But if I have a square and I rotate it just a little bit, 45 degrees, now it's a diamond, and I can tell something's changed. So it's not symmetrical in rotating like that. And so when we're dealing with the forces and the particles, we can do all these little rotations and see where things change and where things don't. That's as deep as I want to go into that. But this helps us link bosons, which is things like photons, gluons, and the Higgs boson, God particle that made news, and fermions, electrons, protons, neutrons, and quarks. While string theory can be any one-dimensional little string that helps create fundamental particles, these symmetries really make the math work better. So we're going to go deeper into this. So when they did the math, they found out that 3 dimensions of space, one more of time, if we want to treat it that way, is not enough room to curl up dimensions and get these strings to make all the particles that we just saw on the previous slide. We need more. We actually need 10 dimensions. Oh my goodness. What about these 6? Anybody fall into another dimension recently? No, that doesn't happen. That's good. These are curled up. They're very, very tiny. And a classical way to use it, I'm coming from Brian Greene's example back in his Elegant Universe video days with Nova. If you look at a power line in the distance, you see a single line, a one-dimensional strand. If I go up to it, I can see that it's got a circumference. It's got another dimension, a second dimension that is curled up around it. And so a little ant could walk around that. So it looks one-dimensional until you can examine it close enough and see that you have another dimension there. Okay, so first dimensional, second, third dimension, on like that. Problem is, how is it going to be, how do you curl up these little dimensions? And 2 Chinese mathematicians, last names Calabi and Yao, asked a question. I had a little strip of paper up here. Did someone clean that up?
Sorry, I cleaned it.
Is it in the trash?
Right here.
Right here? Okay. Thank you.
Didn't realize it was a prop.
It's a prop. You're fine. I'll give it back. All right, so what they were asking mathematically is, how can we do anything we want with a Mobius strip? Anybody know what a Mobius strip is? You do? What is it?
We can play what we want, just like we can do whatever we want to.
Okay, all right, that's good. Anybody else? Mobius strip? Okay.
Isn't it like a strip where if you travel on the surface, like on the outside, then you'll end up on the inside surface?
Absolutely. Yeah, so here is a 2-dimensional, we'll pretend it has no thickness, piece of paper. And if you do one simple little thing, you use the 3rd dimension to bring it around with a twist. Let me get it right here. There we go. I've now taken a 2-dimensional piece of paper and I've curved it in the 3rd dimension, 1 dimension higher. And it before had 2 sides. If I write like he wrote on one side, there was no writing on the other side. But if I put my pencil down now and then trace around, I'll come right back to where my pencil was. So by taking some dimensional object, bending it in the next dimension up and twisting it, I now get rid of one of the sides. Very simple. And they asked, what if I put in any number I want for the number of dimensions? You curl one higher and you take away a surface. And here's a kind of graphical picture of what some higher curling is. And when the string people came along and needed a shape to curl up these dimensions, these fit the bill. They were just asking a general question in math, but it became useful in string theory. So down at the very smallest scale in the universe, when you can't get any smaller, this is how small this is. It's a period with 35 zeros and a 1. It's really small. It's called the Planck scale, and it is the smallest we can go. So if you fill space like this, and then you look at a tabletop and take a little teeny part and magnify it, a little teeny part and magnify it, a little teeny part, magnify, 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 you're almost down to that 10 to the minus 35 meter size. You can start to see some wiggles there. But if you get all the way down there, the math right now, combining quantum mechanics and general relativity, the two big pillars that science is sitting on, it's just a mess. You get infinities and pieces breaking off and things that come in loop and tear, and it's crazy. But if you put these little strings down here all curled up, everything becomes calm and nice, and the math doesn't go crazy on you. So that's the hope, and that's the glimmer of what they're seeing as they've been looking at string theory. So if you have two electrons coming in and they're going to hit each other and react, that's happening at this single point, and that's pretty violent. But if you have two little strings, kind of like rings on a finger, traveling through time and meeting each other, it just kind of become the new particle. The reaction is much less crazy. That's great, but then as people started jumping on that, they found 5 good string theories, all working in different ways. They all have all these interesting names. And so people started to get despairing again, like, well, we want one theory of everything. Now we got 5. And there's so many theories that could come out of this. Well, along came a guy named Witten. He added one more dimension and showed that they actually are all aspects of the same M theory. He's never told us what M stands for. Some people think it's magic theory or master theory or it's his first initial W upside down, but we don't know. I was almost going to skip this. It's not too funny, but I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. Okay, what would that imply? I don't know. All right, there you go. So they've talked about string theory as going through revolutions. Every time another breakthrough happens, it helps them go forward. So here's kind of the timeline of what I've already said. String theory came out of mathematics in the 1960s and was worked on through the 70s. Then things sort of stalled. First revolution gave us 5 separate theories. That was in the 80s to 90s, and then things sort of stalled. Then Witten came along in the late 90s to the early 2000s, came up with M theory, pasted them all together. In there we also got some other cool hints of things going on called the holographic principle, not matter in this talk. And things kind of stalled. And what's next is Swampland. And could this be the third revolution? We'll see. Because in this latest time that it stalled, some physicists started to get kind of angry at string theory. Lise Simon, Peter White, and others started giving talks and writing books. Basically, it all boils down to this. If a theory cannot make predictions, it's not physics. And if you can't make observations of what's going on, 10 to the minus 35 meters, it's not physics. It's just philosophy or elegant math. But that didn't stop scientists working on it, but it did damage public opinion. And that's why I have the title I do for this talk. So did you read this talk's advertisement and ask, what? Is string theory still a thing? All right. So I got a few hands. Yeah, good. That's the goal. So we're going to take a look at this swamp theory at the end. Let's keep on now explaining all the parts. So when swampland was proposed just in the last couple of years, or maybe even less, someone did discover one more theory to tie into M theory. So now we're up to 6 rotating theories that all are different branches of M theory. And just to assure you, I'm not going to get into the math of this new swampland stuff. It is some of the most advanced mathematics I've come across. It is even Sean Carroll, I think, was struggling at times to keep up with his guest when we were talking about this. But what we're looking for are swampland, which is places where you're not going to find a theory that works. Don't even spend time doing it. Because going into this, with M theory, all the ways you could plug in the numbers and try to get a universe out of it, there's about 10 to the 500 possible solutions. That would take a very, 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 very impossibly long time to find that needle in a haystack. But the swampland is the places you don't need to go. It's swampy. Where you want to go is the landscape, where you can find, stop doing that. You're so bad. You want to go where the landscape is, where you can get some good solutions. And in there are jewels where everything seems to work wonderfully. Right? So is there a way to divide out that 10 to the 500 avenues to go and get this down to something we can tackle? All right, so again, the goal is general relativity, Einstein's theory of relativity, and quantum mechanics, the super successful, better?
Slightly pardon.
Oh, thank you. Nice. And that way I'll just keep my finger on the arrow. If you just jam general relativity and quantum mechanics, you get that foamy, crazy, broken world down there, and the math doesn't work. And one of the big problems we have is gravitation. How do we get gravity in here? We don't have a theory of what's called quantum gravity. Gravity comes really well explained in Einstein, and we ignore it in quantum physics. You just don't need it. Nobody needed gravity to predict the Higgs boson, and then 47 years later, they discover it and see it. Gravity didn't matter. All right, so let's go back to the earlier list that I had. I left some things out. Again, gravity and the graviton. We've never seen the graviton, and we don't know how it works in this quantum world, down to the tiniest particles. And there's something called dark energy out there. Oh no, we've got another big thing that we don't understand. And we have something called dark matter. The reason we have dark on there, because we don't understand it yet. That's all that the dark means. It's a placeholder for super fizzy particle or whatever, I don't know. So they name things weird. There's charm, and there's strangeness, and there's things like that in quantum mechanics that I think they stayed up too late at night and didn't have coffee. So, all right. So some review and definitions. We want to explain this dark matter and dark energy. What is that? Well, let's start with dark matter. Dark matter was discovered by looking at the rotation speeds of stuff in galaxies. And in our solar system, Kepler's physics works great to explain why the planets are going around. Pluto's going a lot slower than Jupiter. Jupiter's going a lot slower than the Earth. Things closer to the sun go quickly. And so in our galaxy, things go quickly in the center, and then suddenly it flattens out. The velocity just stays the same or close enough. So it acts more like a vinyl record than a solar system. Well, that's not right. That shouldn't be happening. I used to have to say record, what's that? Now everybody loves records again. So everything that was old is back around, and I can use it as an example. Yeah, so it's acting like a solid, and that's weird. So let's take a look at that. So we expect Kepler's stuff to work, and it falls apart at the outer edges. And the explanation for this is it acts like there's a dark matter out there. The reason, it's another reason I guess you could call it dark, is it doesn't do anything with electromagnetism. It doesn't play in the game of light. So light goes right through it. Does nothing to block or absorb or re-emit light. It may not work with the strong or weak nuclear forces. There's some versions of dark matter where two dark matter particles are actually antiparticles for each other, and they would release a gamma ray photon based on a weak nuclear reaction, but too much. We don't think it acts with that, it just works with gravity. And it could extend as far as 7 times the visible radius of the galaxy, and even have 10 to 100 times the mass of the galaxy that we can see in light and dust and stars. It's crazy. So here's a picture of, could be our galaxy, way down in there. That's 150,000 light years across. And we are out here in the galactic suburbs. We got a halo around us of globular clusters and different population of stars. And then here's this huge bubble of dark matter around us, weighing a lot more than all that stuff in the middle. To not understand that yet keeps astronomers up at night. It really does. We can see dark matter do other things, like here's a cluster of galaxies in the near us. These ones that are kind of oval shaped and nice looking are all together forming a cluster with a lot of dark matter in there. That turns the bubble of space that they're in into a lens. If you've ever seen like a globe or some sculpture made of glass, and you see people walking on the backside, they're all distorted and warped because that's what light does, is it goes from a gas through a solid and then back to a gas and then into your eye. So that streak right there, and this blue one over here, and this bluish green one here, and that one right down through there, and right through there, those are very distant galaxies being just warped out of shape from our point of view, sorry. So that's dark matter in action. It's bending space, and it's bending the path of light through space. So kind of hard to ignore. Here's another good example, a famous one called the Bullet Cluster. These are kind of 2 low density galaxies that collided and went through each other. Believe it or not, if 2 galaxies collide, and the Andromeda will collide with us in about 5 billion years, so don't panic. Don't sell your stock. The chance of 2 stars hitting is very low. But looked at infrared and with looking at the distortion of background stuff, the pink here is the dust that the 2 galaxies had that got pulled together because gravity holds it together. There's friction there, and that yanked the dust out of the 2 galaxies. They'll probably go around and come back and collide again. But the computer has added a bluish color to where the distortion shows where the dark matter is. The dark matter doesn't care about gas and dust, things with friction, operating with electromagnetism. They're still going their own way with their own momentum. All right, let's switch over to dark energy and talk about what that is. All right, so we have an expanding universe, and what goes up eventually should come down. And so this is 1998 that this discovery came out. 2 different teams were looking at different kinds of supernova. Spectra get to us, showing us their velocity as compared to their distance to us. And when they plotted it, we see the galaxies in the past were expanding away from each other much slower than they are today. And that was the last thing on anybody's mind. They were expecting maybe nothing. A constant, we call the expansion rate of the universe itself the Hubble constant. That means it's not constant. And we were expecting maybe it slows down at present day. Gravity's starting to pull things back, slowing the expansion. It's accelerating. And they all had to go back. I think a graduate student did the first calculations for one team, and the advisor went, "That's ridiculous. Go do all the calculations again." But it was true. The universe is expanding as accelerating as it expands. And that it takes energy to make things expand, so we stamp dark energy on the phenomena and hope we figure it out. When you look at the best picture of the early universe, the cosmic microwave background radiation left over from the Big Bang, we can see how matter is distributed. We can look at how matter is distributed now, and that also supports this accelerating expansion. So, one thing that this could be related to is that when the universe started cooling, if you get vapor in the air, that's a gas state of water. Start cooling it down, and now you get water, liquid, rain. Cool it more, and now it's going to switch to a solid. It goes through what's called phase transitions. So the universe, as it cooled through the Big Bang, we think went through some phase transitions too, and a bunch of families of particles cooled out. But when it got to the end, it didn't sit at the lowest possible energy. It's sitting up here on this little hill in this graph. So empty nothingness. Far out into the universe you can go, as far from any galaxies you possibly can. Maybe there's one atom in a cubic mile of space. There's a lot going on. There's a lot of energy. These are called virtual particles. And out in nowhere, they form constantly, and they are particle and antiparticle of each other. They separate and come back and meet each other. And they go away faster than we could measure. So we also think that this is really what's going on inside of atoms, making atoms work. This is what makes air have pressure. Just about all of reality is around us is built on this. But even in the emptiness of nothing, this energy could be contributing, to this expansion and acceleration. We can measure this in the lab. The scientists who did it first, last name Kashmir, so that's what we call it. And so these little particles are forming every place in this little vacuum chamber with two really perfect plates with a little gap between them. And as you get them closer and closer and closer and closer, out here, the particles can form and disappear in any direction they want. But in here, you start taking away the direction in the plate. The plate starts keeping it from being able to go in the plate-to-plate direction. So that means there's fewer particles forming. And if there's fewer particles forming on the inside, then you're going to have a push from the particles outside pushing the plate inward. So there's a force that we can measure on a tabletop. So this is part of everything around us. Another place that this is interesting, and this is going to come back in the end, is that here's the edge of a black hole. And these little virtual particles form out here all the time, but if one forms right on the edge, one goes in, one goes out, they don't get to meet each other again. They go, ah! And basically this puts negative energy into the black hole. That takes energy away from the black hole. Anybody know who discovered that? Yes. Hawking, Stephen Hawking. This is Hawking radiation. That this little particle that comes out is taking energy away from the black hole. Black holes do eventually evaporate. Nothing can come out of the black hole by itself, but energy can be robbed from the black hole through this phenomena, filling all of space that might be related to dark energy. All right, so dark energy, to sum that up, is a property of space itself. It's a constant everywhere. We don't think dark energy concentrates more here or less here. It doesn't care about anything else. It says this is a big volume of space, and it's going to be the same here as all the way across the universe. Einstein actually stuck this into his equations and called it lambda because the scientists of the time, the idea in everyone's brain was the universe isn't going to change. Galaxies are just sitting all here, all nice, and they're not going to move. They're not going to get, maybe a few will get closer to each other, but others will move away. It's a static universe. And then he found out that his own equation said, it's got to be either expanding or contracting. There's no way to just balance everything perfectly. So to make his idea in his mind, and most physicists at the time, he stuck lambda, the Greek letter, in there and called it the gravitational constant. No, not constant, sorry. The expansion rate. And he put the value in just right to make it 0. All right. And that was kind of fudging things. And then along come the astronomers and they start measuring nearby galaxies and faraway galaxies. And the faraway galaxies are all going away very fast. And the nearby galaxies are going away kind of slowly. But it's like we haven't had a shower as a galaxy. Everybody's leaving us, except Andromeda. It's coming. So we put the term back in, and now we have to figure out what it is. What is that lambda? When we went to quantum physics and said, let's calculate how much of this expansion should be out there, how much lambda should there be, it predicts a huge amount. How huge? It's the biggest mathematical error in all of science. It is how much we should have dark energy is a 1 with 122 zeros after it. I'm going off the wall. A Google is 10 to the 100. Like, oh, that sounds like something I know. Yeah, Google was named after the number Google, 10 to the 100. They spelled it wrong. G-O-G-O-L is the original, so when they got the domain and trademarked it, they spelled it a different way. But they were trying to get a Google amount of information categorized for all of humanity. So that was their original goal. All right, back to this. So the universe is accelerating and we don't know why. If you look at the energy budget of the universe, everything that you can see and know are made of is about 4%. This dark matter is 23%, and dark energy is 73% of the energy of the universe, the content. Not understanding all this is pretty embarrassing. So, yeah. All right, so let's move on to a little harder stuff. Back to that supersymmetry. What is that? We call it SUSY. It's a theoretical idea in physics. It proposes a balance or symmetry in nature. Remember my square and my sphere. And it helps us link fermions and bosons. So the idea is, and we haven't seen this yet, the idea in supersymmetry is that there's a partner boson. For every fermion, there's a partner boson. For every boson, there's a partner fermion. And the superparticles are called sparticles, because that's cute. If you have a superparticle of an electron, it's called a solectron. So you just add the S for super. If you're going for the photon, which is a boson, it would have a superpartner called a photino. You just add eno on the end. Take the O off, I guess. And that is a fermion. So if you get superparticles, then we're on the right way to solving the problem. But at the Large Hadron Collider, we've been looking since we've announced the Higgs boson, and they haven't seen any hint of superparticles yet. That's what it's doing now, and it's been doing for years. All right, so supersymmetry is like a cosmic choreographer, ensuring that the universe particles and forces are balanced in a way, and it also is incredibly useful in string theory. All right, it stabilizes the math. It naturally emerges from supersymmetry, or it requires those extra dimensions, those 11 extra dimensions, and it unifies forces and particles through these superparticles. So we really want to have supersymmetry to be real. It would be nice. All right, so let's get into the swampland now. A lot of energy around us. The universe isn't super hot, and it's effective in describing the universe we're in, and that's what we're hoping for. So landscape is a good place to land. We want to eliminate the swamp. So these effective field theories, I'm just going to call them EFTs, not all of them are compatible with quantum gravity. Well, if it's not going to help us with gravity, throw it out. And so swampland is what has all those not compatible gravitational theories. Don't even look at them. Don't spend the time. All right, so here's string theory, and we're trying to map it down to landscapes that we can discover. And it's very much like an ocean voyage. You're going through nowhere, and suddenly you come across an island where there's a lot to explore mathematically. So that's encouraging. There's another way. My earlier slide with all the particles and the forces is called the standard model, and it's a little part of a joule in the landscape of other good theories that we haven't discovered yet, but we can ignore all the swampland out here. Trying to keep it understandable. If you like graphs, that says the same thing. All right, moving on. So a landscape is consistent with effective field theories from string theory. Swampland is things that are consistent but not realizable. All right. Here's some of the heaviest stuff I got to go through. Something called the weak gravity conjecture. Now, gravity here is weak. I know if you fall downstairs, you don't think so, but it is. It's super weak. The example I always use is if I have a 5-cent magnet from the refrigerator holding up the kid's report card. Oh no, it's all digital now in PDF. But holding up some piece of paper, I can put a little paper clip here, go click, and just pick it up with no effort at all. My electromagnetic muscles have no problem picking it up. And if you think about that little paper clip, the entire Earth worth of gravity is trying to hold it down, and it just failed. And so that's how weak gravity is. Fantastically weak compared to all the other forces. The distance conjecture is important in figuring out what is swampland and not, and I'm going to do that in the next slide. And something that is called the satisfies the no stable de Sitter vacua conjecture. Okay, see, I think scientists use terms like that for job security. So they don't want you guys to go and take their job. It just means that the universe is expanding the way ours is, expanding and accelerating. All right, so the distance conjecture is the weirdest concept I need to get across to you guys. It's any consistent string theory, so that's good. That's what we're looking for on the landscape. If you move an infinite distance in field space, so you're just changing your numbers in what particles have qualities of, and I don't want to go any deeper than that, out of the mathematics you get a tower of light particle states. That's our superparticles. Yeah, so you get that. But the low energy effective field theory breaks down. All right, so let's move on. These tower of light particle states, you, in the mathematics, get an infinite progression of these things getting lighter and lighter and lighter as you go away from the particle itself. This concept is central to Swampland program and has deep implications for these effective field theories that are consistent with quantum gravity. If you get the tower, you're in the swamp. So the question is our universe in a jewel spot? Is it near a swamp? Or it's probably not in the swamp, or we wouldn't have any physics at all, and we wouldn't be here. All right, so why the swampland matters. It impacts building cosmology and particle physics, and there's a lot of field theories out there that people are working on that might already be provable. You guys quit, stop doing that, you're wasting your time. That's a dead end in research, and we had no way of knowing. People are just poking at numbers and trying. So it promotes more constrained and testable theories, and remember, we want something testable. All right, so I said earlier, we have weak gravity in our universe. We were able to discover the Higgs boson without having to care about gravity. And the distance conjecture is another way of saying that. Once you add four-dimensional gravity, you cut off a large number of those, remember the SUSY symmetries that we're using? It takes a tremendous number of them away. They're all instantly swampland. We number them, actually. We shorten it to SU. SU1 up to SU23 can give you good stuff. SU24 all the way up to infinity are now ruled out. We've just made some serious progress in getting rid of the 10 to the 500 solutions that we can never make our way through. So that helps. We can turn to black holes and get rid of some more, discover some more swampland, and maybe get closer to some landscape. So black holes are huge quantum gravity machines. We don't know how relativity and quantum physics work together, but black holes do. So, and they're doing it all the time. If you're curious about the picture here, I'll stop a second for a side. When the movie Interstellar came out, Nolan wanted the most accurate picture of the black hole that astronauts would see if they went near one. And so physicists gave him all of Einstein's equations and showed him how to do it. And he bought a tremendous number of NVIDIA cards and hooked them up and calculated like crazy and came up with the first real simulated image of a black hole. Remember, gravity bends space and makes it just like a lens, just like those big galaxies are doing. A black hole does it too. So here's matter falling in to the black hole, getting heated up and spinning around in what's called an accretion disk and spiraling into the black hole inside. This arc over the top and arc under here is just the warped image of the backside of that disk. It's being warped over so you can see it out here. So yeah, the simulation for the movie's special effect was so accurate that they actually published scientific papers on that special effect. All right, so that's just a fun side. So they have large amounts of entropy. That takes us back to Bekenstein and Hawking again. And entropy is linked to flow of time and also the expansion of the universe. As the universe expands, you have increased entropy as time goes forward, and as everything gets pulled apart, information gets more scattered, and all sorts of different ways to say the same thing. What's interesting is when you're looking at the entropy of a black hole, its value is equal to 1/4 of the Planck area units that make up the surface area of a black hole. So you can link gravity and quantum sized effects. Remember that those little strings are down there at the Planck scale. So I don't know, that 1/4 is just really weird. Again, a really clean number coming out of science, you start getting suspicious that something is happening. So large distance physics, relativity, and high energy, low energy particles all get linked. And this gives us the landscape, and we're not getting a swamp looking at the physics of a black hole. All right. And gravity really is different than other forces. It's causing us to think differently about these things. The weak gravity conjecture, again, is very powerful, more powerful than gravity at any given distance in math. So the charge matters a lot more. All right, let's go back to Hawking radiation. So eventually a charged black hole will evaporate down until it gets to the last particle. It's just like the last drop in your favorite beverage. And if you've come up with a string theory that if you run a black hole forward in time, it eventually evaporates right down to that last little particle, you've got a jewel. You've got a place on the landscape that's a jewel. Anytime you're doing the math and you don't get a nicely evaporating black hole, throw that away. It's swampland again. All right. So are we near one of these jewels? We probably are kind of close, but we'll find out. When you choose extreme values in the string parameters, you always get a working universe. And dark energy prediction, remember, is 10 to the 122 power off. So maybe we're not near a jewel. There's some big, huge error here in the distance between what quantum mechanics predicts lambda should be and what it actually is. This range is huge, but the error, when you just take a look at lambda itself, turns out to be between 1/2 and 1/4. Oh, there's that 1/4 showing up again. We don't see a light tower of particles in the standard model, but there is dark matter. Maybe there's a direct link between dark energy and dark matter. So when they did the math, working with lambda, the expansion rate of the universe, looking at all the experiments and looking at galaxies, looking at rotation of galaxies, looking at collision of galaxies, looking at clusters of galaxies, warping background stuff, everything is rolled out except that 1/4. So we're coming into the big conclusion now. This means that one of these curled up dimensions, we had our 7 additional dimensions all curled up like the ant going around the distant power line, but they're curled up at 10 to the minus 35 meters where we could never do any math or physics with them. One of them, gravity, might actually be only about 0.0001 centimeters. curled up in a space that big. So instead of 35 zeros, you're only down 3 zeros. Well, that's the size of a dust particle. So now it's not a physical impossibility to measure this and see. Now it's just an engineering problem. It's difficult. I mean, the entire Earth makes this much gravity. What is the gravitational pull of a speck of dust? Well, it's not impossible that we can make that measurement eventually. And what we're actually interested in is a little different than that, but I'll get to that in a second. So we also, someone noticed that neutrinos, another particle on our standard model, has a scale related to that lambda based on 1/4 again. So the cosmological scale is lambda to the 1/12. The weak scale is lambda 2/12. The neutrino and dark matter scale is lambda 3/12 to the 3/12 power. And the Hubble scale, just the expansion, is lambda 6/12. And the 12 comes from 4 dimensions of space-time times 3 coming from a formula NH cubed, the cube power of the Planck scale, to give us volume of space. So I just jumped hundreds and hundreds of pages of research paper, but the fact that we're getting the expansion rate of the universe, dark matter, all these fundamental forces and particles can be linked together through just lambda to something over 12 is a tremendous unification. It's huge. And when they do the math backwards, it actually predicts the correct amount of dark matter. You don't have to tweak it. You don't have to stick in a fudge factor. And it's cold dark matter, just that we are expecting to see. So maybe instead of a tower of light particles, we have a dark tower of particles. You don't see them. They're all invisible to looking at it in a telescope, but they're there doing that whole Swampland test. So to prove this, we just have to see if gravity, which holding the moon around us and us going around the sun and you jumping up and down on a powder puff field, all obey a 1/r squared, 1 over the distance squared between you and the center of the Earth, or the center of the moon to the center of the Earth. Down at the size of a speck of dust, maybe it becomes 1/r. Maybe it's 1/r cubed. We don't know, but that's the experiment we need to do. We need to feel how gravity acts around a speck of dust. Extremely difficult, but not impossible. So can we say the dark energy is not a cosmological constant? Is it stable or not? When you go to extreme ranges, this says it isn't. So we're close to one of these joules, but not exactly on. And the dark matter and dark energy is that infinite tower of particles that we just haven't seen because they can't see them. They don't respond to the ways we sense stuff directly. So the expansion of the universe probably will shut off in less than 1 trillion years. I won't be here for that, but and observations can tighten that number down. Dark energy will go away at some point in the universe's future. So critics say, well, it lacks rigorous proofs. I think the math is pretty compelling. There's a potential conflict with observations, like if we get more refinement on dark energy, or if we look at gravity at the scale of a speck of dust and it's still r squared, and we got problems. And the debate over size and relevance of the landscape is there too. Like, if you just focus on joules, ignore the landscape, we can narrow it down more. But the scientific community is just starting to chew on this. And that's why Estes Park is probably the first public presentation of this, and you guys are the second public presentation. I can't find anybody on the internet that's tried to boil this down to a public audience. So. All right, so concluding, superstring theory aims to unify all these fundamental forces. So the Swampland project offers consistency tests for quantum gravity. We have a testable approach to linking dark matter and dark energy to gravity itself and string theory. If you want to look at this stuff and read really hard papers, these are the top people in the field that are writing papers on this right now. But urge you to always stay curious and critical. Huh?
So, Laura Anderson is doing any connections?
Who?
Laura Anderson at Virginia Tech.
I'm unfamiliar. Yeah, I'd have to see what she's doing. Questions? Oh.
Really good Star Talk with Tyson and that you did in the last 2 months
Okay.
on YouTube.
All right, I'll hunt that up. Yes, question.
Sorry, is the Swampland project basically like a theory about how to find theories? Like here's like where the opaque theories might be?
Mm-hmm.
Okay.
Yeah, and their first foray into this seems to have already found some pretty significant interesting stuff, yeah. And it definitely brings string theory right back to life. That's why I say, is this the third revolution? Yeah. So any other questions?
What were the names of those new discoveries then, of interesting places that you're studying? We have jewels already.
Right. Well, they say we were on the edge of a jewel. In our standard model, it looks like we're in a jewel. Everything's fine. There's no superparticles. And Large Hadron Collider's not finding them. But this dark energy, dark matter does have an infinite number, a very high number of dark matter particles, which could also explain why hunting for dark matter has not worked yet, because there's so many masses of these things that we haven't set up the right experiment yet. Right, because a lot of experiments are looking for dark matter. If we could find that, you got Nobel Prizes all over the place. Yeah. All right. Other questions? Yes. Go ahead.
Sorry, just one whenever you talk about space-time,
Mm-hmm.
does that like assume this like static theory of space-time, like it's all kind of one thing and it's like static?
When you're dealing with the dimensions itself, you're just dealing with the physics, and time is irrelevant to Einstein's theory and quantum theory. You can run the t time forwards and backwards. People have even equated Einstein's work without time t variable in it. And so Einstein's stuff does not need time to flow. The only physics that makes time flow is entropy, and that the second law of thermodynamics, and that gives the arrow of time and a progression of time. And so, yeah, it's an interesting philosophical problem to deal with. I'm experiencing time. I'm late for something right now, but physics says, nah, it's not so important. So, yeah. We were talking out there about a model of the universe in which space and time are just done. You have a Big Bang at one end and the end of the universe at the other end. There's a restaurant there, I think, and deep cut. And so it's called the bulk, and everything exists all in one moment. And my example out there was the concept of now becomes weird. So here's my now right now, and if I think of a galaxy across the universe and I start walking towards it, because of its great distance, millions, billions of light years away from me, its now becomes a century in the future that was now when I was standing over there. And if I walk away from it, now over there is a century back in time from now, where I'm staying still. Oh, now the now is the now that was when I was here. Ooh. And that it comes out of Einstein's equations too. That now is relative. Oh, wow. They should probably call it relativity. Yeah, okay. Any other questions? Yeah.
You sent people into space without even using them.
That is really good. Newton's equations for motion and gravity, all we needed to send all the spacecraft out. Einstein's equations refine it, put in correction, but we're dealing with everything creeping along so slowly, it just doesn't matter. We can be within a couple inches of where we want to be just fine. Einstein's equations, I like to say this in a different talk, but Einstein's equations would have been discovered if Einstein never lived. We put GPS satellites up, everybody's got GPS and maps on their phone, and gravity is making time run slower down here than it is up in orbit. And they're also moving, so that also makes time run slower for them, but it's complicated. And so if we don't have the corrections of velocity and gravitational well depth in the satellites calculating in, then within a week or so, your GPS has you maybe 10 feet over here. A month or so, you're now maybe a quarter mile off. I'm just making up numbers. But yeah, the GPS system would have failed right away. And they could reset, and then it would just keep failing. And they were, there's something in physics happening here. Can't explain it. And so you've got general relativity on your phone. Ooh, cool. Yes?
Speaking of, do you foresee anything like AI or ChatGPT being able to help with anything like this?
That's interesting. Of course, they make up stuff and hallucinate and tons of problems like that. Yeah, it's bad. I wouldn't hesitate to use it to see what you can get out of it. I would build what I'd call a sandbox, and I'd play with it over here and not let it touch my other physics, and see if that leads to anything. Large language models are glorified sentence completers. They're just really good at it, and also flatter you a lot so you can come back more. But yes. And I was teaching an algebra course a year ago, and I had it make an algebra quiz and with answer key. Oh, it's awful. It was not correct. So it's not doing math yet. So maybe I wouldn't trust it diving into physics yet. So.
I mean, maybe it will harness the processing powers that all these GPUs have to calculate things faster.
That's true. Yeah. Yeah, if you could look at landscapes and make more swampland identified through the computing power, maybe there's a way there, yeah. All right, great. I'm willing to hang on for more questions. Go for it.
What's the strangest result that your research has yielded?
You mean in string theory?
In general, in physics.
When I was at NASA, I was their senior science education specialist. So my job was to take everything made for NASA or by NASA that communicates science to the general public or schools, kindergarten to grad school. My job was to make sure the science is accurate, that they didn't explain things with misconceptions. Like if you're going to explain the dew point, I think that's a good way to do this one. The dew point is based on condensation of moisture at a certain temperature, and what people say is how much water vapor the atmosphere can hold. And the analogy they have is if it's a hot day, it's a bigger sponge. If it's a cold day, it's a colder sponge. And when you have a thermal take moisture up into the atmosphere and form a cloud, you're squeezing the moisture out of it, making rain. And everybody has a clear picture of that going on in their brain. Problem is, dew point equation would work on the moon, Mars, doesn't matter your atmosphere, you don't have to have a sponge. It's based on the energy in the water itself. So if they slip into doing something like that, I go, yeah, let's take it back. If you're going to explain that to a third grader, maybe that's good enough. If you're going to throw that into a high school material, no, you can't do it. So that was part of my job there. And then also making sure it was written for the correct audience. So no calculus going to second graders. That's a good thing to avoid. And then I've got some of these at home still. Someone made a pop-up book on active galactic nuclei for high school students. Like, why would they want a pop-up book? That's kind of insulting to a high school student. They spent a lot and printed a lot before they sent one to me. I'm like, whoa. So that was my job. So I didn't do research with NASA. I was just assimilating, regurgitating, processing stuff. The research I really did was in meteorology. So I'm a meteorologist also. So as an undergrad, I worked on the on lightning. So lightning initiation and the processes that go from the very initial instant lightning, how it finds a channel, how the return stroke goes ground up and like that. So we had cameras in Orlando, Florida, lightning capital of the world, with domed mirrors and a camera on a tripod pointing straight down, and using a brand new Kodak 1 megabyte device that cost $10,000. That's how far back, this was early 90s. We videotaped, that's we had to use videotape, lightning occurring. And so it would go into the memory, lightning flash, trigger a stop, it'd fill up with lightning data in memory, and we had to feed that into a videotape machine. That would take me a couple weeks to work through one lightning strike, going frame by frame, plotting where it went. So we came up with the first real detailed little wiggling head imagery of lightning trying to find something on the ground to connect with. As a grad student, I worked on the point area problem in precipitation. So you have rain gauges all around, and they're a single little point looking at rain coming down, but you've got radar or satellites going overhead that are taking an image, but the image has a pixel that maybe is a kilometer by a kilometer, or your radar might be 500 feet by 500 feet pixels. And so how do you relate those two? How do you come up with a way to make radar and satellites more accurate to what you're finding on ground truth? And I identified 8 sources of rain gauge error. I was eventually hand modifying high-end rain gauges, drilling things out, putting sapphire bushings in there, and coming up with a balance checking technique and putting little drops of solder on it to balance the cup, and on and on and on to make really, really accurate rain gauges. And my last research in that, before I moved to NASA, I built a network that was 12 by 12 around Will Rogers World Airport. And this is pre 9/11, so I was able to swipe a badge, drive a truck around, and download data from rain gauges with a runway right there, and planes were right by me. I was like, oh, this is so cool. So it was very loud too when they were taking off. So that's the 2 contributions I've done. I had papers written about back then. Yeah. All right. Any other questions? Where do we have viewing? Awful out there. Oh, so. Okay.
We might find the occasional bright star, but that's going to be about it tonight.
But that kind of make a little sense? Help? All right. Thank you.